good morning, everybody, and welcome back to Science Live. We're here again broadcasting from the Creation Museum in Petersburg, Kentucky, and we're in Discovery Hall today. This is a place where a lot of our workshops take place, where guests can come and hear speakers like Professor Faulkner, who is here again with us today to talk about some astronomy things. And we're going to be discussing the idea of seasons in a minute, but you have any good seasons jokes? We should have talked about this before we got started on.
Yeah, I sort of like Ragdoll and Sherry. They're very good songs by the Four Seasons.
The Four Seasons,
Yeah.
that's
Sherry!
all right. So you kids will have to have your parents go look that up on YouTube.
Or your grandparents.
Or your grandparents, indeed, indeed. All right, so we are ready to get going today. We're going to be talking about the idea of seasons and why on the Earth, represented here by this little globe, we have different seasons. A lot of people think that it has to do more with distances and things like that, but we're going to get organized here and we're going to understand really well how this globe and the way it's set up as a model helps us make sense of the seasons. So we'll be monitoring the comments as well. If you guys wind up with questions, I'll try to get a few of those in as we're working through these things. So go ahead and get started with your demonstration here.
Okay, first of all, we have a globe here representing the Earth, which is roughly a sphere. And one thing you'll notice is that it's tilted. It's got an axis of rotation like this. The Earth spins like that. And it's tilted 23.5 degrees from the perpendicular. I think most people know that. And they know that's very key in determining what the seasons are doing. But again, it's important that you know that's there. Also, we've placed a little green sticker with a number 3 on it. I'm not sure why. The location of Kentucky, which is where we are, we'll be referring to that a couple of times.
We're in the tri-state area.
Right.
I just made that up.
Oh, that's good. I like that. Okay, you're right. The
Where
tri-state
Kentucky,
area.
Indiana, Ohio meet about a mile.
We step
away
outside,
from
we can
us.
see Indiana and Ohio both.
Yes,
It's real easy
there
to
you
see.
go. That's
So-
why there's a 3.
Okay, makes sense. Anyway, that's what we want to start with. Now, we're going to use this, if you want to step back with the camera, we're going to use this smiley face balloon there to represent the sun. And so I'm going to start off with the Earth on this side of the sun. And you can see that the northern hemisphere here is tilted toward the sun. And then the southern hemisphere is tilted away from the sun. Now, what's going to happen is over 6 months, the Earth is going to revolve around the sun like this. And now you'll see it's reversed. Earlier, the northern hemisphere was pointing towards the sun. Now it's pointing away. And the southern hemisphere is pointing toward the sun, whereas before it was pointing away from the sun. And this is where most people stop at this point, because they think, well, the southern hemisphere is closer to the sun here, and the northern hemisphere is farther away, so therefore it's the distance that's causing the season. And of course, when we started over here a moment ago, 6 months earlier, the northern hemisphere was tilted toward and the southern hemisphere was tilted away. So we're having winter in the south and summer in the north. Now that correspondence of where winter and summer are occurring is correct. When you're tilted toward the sun, you have, in your hemisphere, you have summer. When you're tilted away, you have winter. But it's not the distance. It's really easy to think that because most textbooks show a diagram pretty much like this. The sun's right here, the Earth is right here, and they're pretty close to each other. So if you go a few inches on either side, it's a big deal. But this is not the scale at all. Turns out the distance between the sun and the Earth is 12,000 times the diameter of the Earth. This globe happens to be a foot across, 12 inches. So if this were to scale, the sun would be 12,000 feet, nearly 2.5 miles away. Obviously, we can't fit that in this room, nor can we fit this on a diagram on a page of a textbook. So that's a problem. And again, this really causes people to see this all wrong.
We think we've got a little microphone issue here, so I'll hold this one in for you.
All right, thank you. And so people tend to think that it's the distance that's important. But again, if you change this distance by just a matter of inches over 2.5 miles, I think that you would agree that that isn't going to make any difference as far as your temperature is concerned. A few inches over 2.5 miles, no big deal. Furthermore, the Earth's orbit around the sun is not a circle, it's what we call an ellipse. And we have a point called perihelion, where we're closest to the sun, and a point called aphelion, where we're farthest away. Do you know when perihelion is?
Well, if it's hotter during that time, it must be in the summer, right?
That's what most people would think, and it would be wrong.
Wrong.
Actually, perihelion, closest point to the sun is in early January.
For us, that would be winter in the northern hemisphere, but in Australia, it'd be summertime.
Yeah. So if the distance were what's important, by the way, we're closer by about 3 million miles, or about 3% out of that 93 million miles. So if it were distance, everybody would have summer in January, and everybody would have winter in July, which for the northern hemisphere obviously isn't the case. So there must be something else going on, and that's where we want to talk about this today. Now let's start here, and let me turn the globe a little bit. I'll put Kentucky right there, make sure that's level, and let me grab a couple of pencils. I've got a couple of unsharpened pencils here, sort of like me, not very sharp, right?
Not very sharp.
Not very sharp. All right, now I'm going to put a pencil here perpendicular to the surface of the Earth at Kentucky, right there. This is summer for us. In fact, beginning of summer would be June 22nd, what we call the summer solstice. People in the southern hemisphere would prefer to call that the June solstice. All right, and so we have the perpendicular, and then I'm going to make the other pencil point towards the sun. Get my hands all the way so people watching on home can see this. This pencil points the perpendicular to the ground. This points the direction to the sun. Do y'all see that? Perpendicular to the ground, direction to the sun. Now let me orient that for the way you would normally see it. That's the perpendicular to the ground right here. And there's the direction of the sun. Notice at noon on the June solstice here in northern Kentucky, the sun is nearly overhead. It's only off by about 10 or 11, about 11 or 12 degrees or so. That is, the sun is very high in the sky. But what happens on December 22nd, let you get over there. It happens on December.
Let me trade hands.
Yeah, let's get this
We gotta move
whipped
that
around.
the other way.
All right. And now we're talking about summer, the winter for us. So let's get Kentucky on the top again. And there is the perpendicular line once again. And here's the direction to the sun. And notice that large angle there. So if I arrange this so that that's perpendicular, notice the sun is not very high in the sky. And you probably noticed this yourself. You go out on a winter day, and the sun never gets very high in the sky. But if you go out on a summer day, the sun can be very high in the sky. And so the sun is much higher during the middle of the day, particularly in the summer, than it is in the winter. Now let's step back over here to the desk. And I got a nice little demo that I can use with a flashlight to illustrate this. This flashlight is going to illustrate a shaft of sunlight coming in. It's going to represent the sunlight coming in, a certain dimension it has. And you'll notice as it's nearly vertical right there, it'll represent what we see during our noontime in June here in the northern hemisphere. And you can see how much area that is being encompassed by that shaft of light. But if you contrast that with December, the sun's rays are coming in at a steep angle like that. Look how much larger that area is.
So if you think about the other, it was probably about this big. Here we have a lot more area.
Yep. So here is summer, and there is winter at noon. Different areas, but the same amount of energy coming in each case. So if you have sunlight representing heat coming from the sun, it's going to illuminate that much area during summer, but in the winter it's going to illuminate a much larger area. And that, of course, then is a problem because you've got the same amount of energy, but a much greater area to spread it out on. And a comparison I make to is a pat of butter putting on a piece of bread. If the piece of bread's kind of small, single slice, that's not a problem. But if it's as big as, say, a pizza pan would be, then you really can hardly even taste the butter because it's spread out so much. So during our summer, the sun's rays are much more concentrated than they are in the winter, hence it's warmer. You call that the area effect. Now there's another thing we can talk about, I would call the time effect, and I can just leave the globe right here, if you can look at it for the camera there. And you can see this little green patch marking the location of Kentucky. And this is our beginning of summer for us. If I rotate it over here, you probably can't see that green patch. But notice what happens as the Earth spins. It comes across, it becomes obvious. You can see now that green patch where Kentucky is. It revolves across, rotates across like this, and eventually the sun will set. Notice that the arc that this makes is huge. The sun rises, I'll go back again, rises early in the morning here in the northern hemisphere in June. It then is noon, and then it's late up into the evening that the sun will set. So the sun's in the sky a very long time in our summer. But what happens during our winter? Well, it's reversed. If you look over here, you won't see the green patch very early, right? Maybe it's starting to show up now. At sunrise, you have noon, and then the sun sets relatively early, late in the afternoon rather than on up in the evening. So the sun is not up in the sky very long during the winter months. And you probably noticed that. During winter around here, we get about 9 hours of sunshine. And during the summer months, around June, we get about 15 hours, 6-hour time difference. So the sun is in the sky a lot longer, and so you have more time for the sun's rays to heat up the earth. So I call that the time effect between those two.
Okay, so if we think about, I'll slide on over here. If we think about this from the distance from the equator up to the North Pole, we divide that into latitude, degrees of latitude. How many degrees of latitude from the equator to the North Pole?
Kids at home know. It should be 90 degrees.
Okay, so if there are 90 degrees here, we're located at
39 degrees.
39 degrees, so almost a little halfway.
Yeah, almost halfway, between third and halfway.
So what would happen to the sunrise time if we were up in the top of Canada up there?
Okay, you'll notice that probably what you're driving towards is the thing we call the Arctic Circle. And people at home, you can see there, you can see the North Pole is right here. Here's northern Canada, there's northern Greenland. Now watch what happens as we spin around like this, and at midnight, you know, the Kentucky's now on the other side of the earth, but you can still see northern Canada, you can see part of Alaska, you can see northern Greenland, and we call that the midnight sun, of course, because the sun's, the northern hemisphere is tilted toward the sun, and so you're looking over top of the North Pole of the earth. The sun's rays can reach over top, and from the side you can see that as well too. The sun's rays are coming in like this, and they're going completely over the top. But if you do this in the winter months, the reverse happens. In the winter months, the sun's rays are coming in from this direction. I'll use my pencil once again. And you can see that the sun's rays are coming in here, and this is going to remain in darkness over here.
So if I'm anywhere inside of this circle, the sunlight isn't going to shine on me.
That's right. I can spin it around. You can see the sun is going to be knocked off right there, right around the point of the Arctic Circle. Now, down in the southern hemisphere, I can't show it as easily because I've got this thing wired down, but down here there's an Antarctic Circle. It's completely analogous to what we have up above. If we spin this as before, then the sun's rays come in, and during their summer months, you can see that Antarctica is largely illuminated. It's reaching. It may not be very high in the sky, but the sun will be up for 24 hours, just like it was in summer months in the northern hemisphere. Now, if we go to winter, flipping it around like this, and we spin the globe, you will see that the sun's rays coming in from your right there are not going to make it to Antarctica, except on that Antarctic peninsula, and only for an hour or two every day. So that explains why midnight sun and at least 24 hours of total darkness.
Yeah. Okay, so if the sun is always shining on the Arctic during the summer months, then why doesn't the ice melt? And the answer goes back to the question of the area effect that you explained earlier.
And it does melt some, by the way. It's just you've got a big buildup, and every winter the ice pack in both hemispheres, they will grow and shrink, but they generally don't go away because it's just too much ice, and the area effect is just really killing it because the rays are coming in at a grazing angle.
Yeah, and as they come in, they're going to absorb some of that, but a lot of that bounces back into the atmosphere as well.
Because ice reflects very well, about 90% falls on it.
Yeah, so we don't get the ice caps melting as rapidly. Okay, so somebody asked a question about fall. So you just talked about a time when in the summer, what's the difference between an equinox and a solstice and those types of things?
Okay, very good question. I kind of glossed over that. During fall and September and March, when we get to the equinoxes, the Earth is not oriented like this or like this. It's oriented like that. And well, the sun's rays would be coming in.
Coming in from this side.
Coming from this side. This would be the northern hemisphere, southern hemisphere. Sun's rays are coming in, and notice that that half the globe here, from pole to pole, is fully illuminated at one point at noon, particularly. But you can see half the Earth there. As the Earth spins at that point, the sun is going to rise and set for every location on the Earth, except right at the poles, and it's just be hugging the horizon there. And so at that point around the world, you have 12 hours of daylight and 12 hours of night. And the word equinox comes from equal night and day. Equinox, that's what the name means. So that's a period of time when the sun, the earth is tilted. It's tilted in an odd direction like this. It's hard to describe in 3 dimensions here, but there is no tilt effectively at that point. Of course, you don't stay there very long because the earth treks through that. And here we just went through the equinox just 10 or 11 days ago. It was on the 19th of March this year. Mm-hmm. So in the northern hemisphere, we're getting on up into spring, and it's autumn now in the southern hemisphere.
Okay, so this year was unique because we had a leap year,
Mm-hmm.
and so I think the 29th of March is probably the earliest.
19th.
Oh, I'm sorry, the 19th,
Yeah.
yes, because the 21st is typical,
Mm-hmm.
20th or 21st. So the 19th was the earliest that can happen because we had an extra leap day thrown in there to throw that back.
And then it all depends on where you are on the earth, what time it is. It's a very complex sort of thing, but it doesn't happen on the 19th very often. Mm-hmm. And as we get on into the 21st century, it's going to be less and less common for that to happen.
Absolutely. So as we think about all of these pieces, does any of this, as you think about this again from an evolutionary view versus a biblical view, does any of this help point you to a creator or a designer, the God of the Bible, who's done all of these things?
Oh, absolutely it does. We talked about the distance not being a factor in the seasons, really. We also mentioned that we're at perihelion in the southern hemisphere summer and the northern hemisphere winter. And there's a design aspect all over that, because you see that if you think about it, if the southern hemisphere is closer to the sun during their summer, you expect their summers to be hotter than northern hemisphere summers, and you expect their winters to be colder because they're farther away. That makes perfect sense because you're about 3%, and that does make a difference. But if you check temperatures between the northern and southern hemispheres, they're about the same. There's no huge swing between the two of them. How can that be? Well, the solution is to look at the two hemispheres, and I'll hold it up like that. There is the northern hemisphere for you. People at home see that? Now, I can't really show this so well because I've got the base in the way.
The base is on there.
But look at...
Will this swing? Yeah, this.
Well, I've got it wired for a reason. I'll tell you about that later. But as it turns out, if you look at the northern hemisphere, it's about half land and half water, maybe more land than there is water. You've got most of Asia, most of Africa, a little bit of South America, all of North America. But if you look at the southern hemisphere, and again, you really can't see it, but spin it around, you can see it. You've got Antarctica, which is the second smallest continent, Australia, which is the smallest continent, a little bit of South America, which is the third smallest continent, followed by just a little bit of Africa.
Yeah, a lot more ocean space in the Pacific area, especially, and then down in the South Indian Ocean.
It's about 90% water. Mm-hmm. Now, one of the things we maybe ought to do a program on at some point is the amazing properties of water. Have you done a program on that?
We're going to.
Okay.
Have that one planned, absolutely.
Okay, one of the neat things about water is it has what we call a high specific heat. And what that means is it takes a lot of heat to raise the temperature of water. You've heard that a watch pot never boils? Well, that's why, because it takes a lot of heat to get it to boiling point. In fact, does water have the highest specific heat of any substance?
No, but it's one of the higher, yes.
But I think there's only one or two things that have a higher specific heat. There's a physical reason for that we won't go into. So it takes a lot of heat to heat it up. And you may know from geography class that cities, locations near large bodies of water have very moderate temperatures. You know, in Chicago, they give you typically 4 temperatures in the area. They'll give you at O'Hare, they'll give it Midway, 2 different airports in the area, downtown the studios at the lakefront. And a really hot day in the summer, there could be a 20-degree difference. Yep. And during the really cold day in the winter, there can be a 20-degree difference because on the lakefront, it's always milder. And San Diego is very mild temperature because it's on a large body of water. Mm-hmm. Well, the sun's rays take a long time to heat that water up in the summer. And about the time it finally gets it heated up, it's now winter, and it takes a long time to cool it down. So you've got the perfect situation. You've got the hemisphere that has the most water, which just happens to be oriented toward closer to the sun during their summer. And I don't think that's a coincidence at all. I think that is the design aspect. If it were done any differently, then it would be disastrous for us, I believe. The temperature extremes would be much greater.
All right, so all of these things just remind us that God has created an earth for us and a solar system that is just amazingly designed with all of these details. the chance that all of these things could happen and then create all of these things is astronomical. And there's no way that it just happened by chance. So we can praise God for the way he's designed the earth, that it's the water that is there to stabilize the heat balance and all of those things, that the sun, we're in what we call the Goldilocks zone, the distance away from the sun to keep the temperature just right. And all of those things are because he created the earth for man to inhabit it and for his creatures to live on it. So we can think about all these things and enjoy the seasons and the temperature differences. Unless you live on the equator, then it's pretty much constant. But we can enjoy all those things and know that they're good gifts from God, and that in Genesis 8, he promised that the seasons would continue. In Genesis 1, he gave us the stars for signs and seasons, and all of these things are just pointing us back to him as a great creator. So thank you for joining us today. We want to remind you that we've got more live streams coming for you today at noon and 3 and 7, and make sure you check those out, and just encourage you all to get out and explore God's creation.